Hi students, in this video we are going to start section 1.4, the divergence and integral tests. So let's first take a step back and review what we have done on section 1.3. So in section 1.3, we learn geometric series and telescoping series. Those are two specific forms of series that are easy to evaluate. For example, for geometric series, if you know that geometric series has a common ratio r such that absolute r less than 1, then you know that the limit is a over 1 minus r. So that is what I mean by easy to evaluate. So you can compute limit of the series easily. But unfortunately, most of the time it's going to be difficult or impossible to compute the limit of the series, right? Well, in that case, we will not give up. So we're gonna just change our focus from computing its limit to just checking that the series is convergent or not. So to sum up, from now on, we are going to just change our focus and just ask a simple question, yes or no. So by this I mean, given an infinite series, we're gonna ask the question, does it converge? And if the answer is no, we're gonna say that the series is divergent and there are no more questions to ask. We're not going to ask, okay, what is the limit of this series? We're not going to ask. We just want to know that the series is convergent or divergent. That is the goal from now on. So we're gonna learn different tests from now on, which is the divergent test, integral test, and then ratio test, root test, and so on. So those are the technique that we're gonna use to check if the series is convergent or divergent. Alright, let's start by looking at the simplest one first, which is called the divergent test. So let's look at the divergent test here. The idea of the divergent test starts from the statement that if we know that we have a convergent sequence, then it must be the case that limit of a sub n when n go to infinity, this is equal to 0. So we can prove this statement by looking at the proof here. So if you know that the series is convergent, it means the limit of the partial sum exists, right? And that means, well, limit of Sn when n go to infinity must be L, and limit of S sub n minus 1 when n go to infinity must be L as well, because the limit of partial sum exists and they are equal to each other. And then after that, if you simplify a little bit, so you're gonna get limit of an equal to 0 here. So why is this statement that I started here is so important? It is because if you have this statement, then you can use a contrapositive. So what I mean by contrapositive is, well, when you learn logic in high school, you know that if you have statement P imply Q, this is the same thing with not Q imply not P. Well, it means if you have a sequence that is convergent, you can conclude that the limit equal to 0, right? Well, the negation of limit a sub n equal to 0 is limit a sub n is not equal to 0. So the statement that you're gonna have is, if you have limit of a sub n is not equal to 0, then you can conclude that the summation of a sub n when n start from 1 to infinity is not convergent, which means it is divergent. And this thing that I just box it in cloud, this is called the divergent test. the divergence test. Alright, I state it again here. If limit an is not equal to 0, then the series is divergent or the series diverge. So let's look at some examples together. So example 12, well, we want to use the divergence test for this example. Example 12, determine whether the following series diverge or state that the divergence test is inconclusive. Alright, so let's start by question A. Summation of n over square root 9n squared plus 1. So again here, when I see the ratio between polynomials, so what I usually do is just I look at the denominator and numerator. So the denominator you have n squared here, but once you take square root, so you have just degree 1, right? And on the top you have just n, which is already degree 1. So it means the highest degree on the top is 1, the highest degree in the bottom is 1. Well, to compute limit of this thing, so we're gonna just divide everything by n, right? So we're gonna just compute the limit of n over square root 9n squared plus 1. And then this thing is limit of n over n here, and then here I have square root 9n squared plus 1 over n. So I divided everything by n on both sides, on the top and the bottom. And now I have limit n go to infinity. So on the top I have just 1, right? And in the bottom I have square root, so 9n squared plus 1, and then I trying to sneak n into the thing under square root, so I have over n squared here, right? Because I just put n inside the square root side. And then after that I have limit n go to infinity of 1 over square root 9 plus 1 over n squared. Now I can compute limit easily because this term goes to 0, right, as n go to infinity. So it means limit here gonna be 1 over square root 9 plus 0, which is going to be just 1/3, which means the limit of this function is not equal to 0. So by the divergence test, summation of n over square root 9n squared plus 1, n start from 1 to infinity, diverge. So as long as you compute the limit of a sub n and then the limit is not equal to 0, then you can conclude that the series is divergent. The statement is so simple, right? So the hardest part come back to when you compute the limit. Alright, let's do part B. Let's start by computing the limit of 1 plus 3 to the n over 2 to the n when n go to infinity. And hope that if we compute limit of this thing and it is not equal to 0, so we can conclude that the series is divergent. So first of all, I'm going to split this thing into 2 pieces. So I have 1 over 2 to the n plus 3 over 2 to the n, right? Well, this is after we simplify it. And then after that I have limit of 1 over 2 to the n when n go to infinity plus limit of 3 over 2 to the n when n go to infinity. So and the first term, this go to 0 because this is geometric sequence, right? And then the bottom is heavy, so 1 over heavy, this thing is the limit is 0. And then after that plus So you have 3 over 2 to the n. Well, this is a geometric sequence again, but your r is bigger than 1, right? Because your r is 1.5. So this thing, the limit is infinity, right? So that means this thing is 0 plus infinity, and it is clear that this thing is not equal to 0. So by the divergence test, limit of, summation of 1 plus 3 to the n over 2 to the n from 1 to infinity is also divergent. Alright, that is pretty simple, right? Alright, let's look at the last one. So I have part C here, summation of 1 over n plus 20. Alright, so I'm going to compute limit of 1 over n plus 20. And then this thing is just, you can see clearly that this is actually 1 over infinity, right? Plus 20, which is 1 over something that is heavy. So actually this thing is 0, right? Because it is super heavy in the bottom, right? So the limit is 0. Well, when you have limit of a sub n is equal to 0, well, your conclusion is going to be the divergence test is inconclusive. So you cannot conclude anything from there. So you have to use another test. Next, we are going to talk about the harmonic series. So first, let's recall the divergence test. So this is the statement of the divergence test. So if you have limit of a sub n is not equal to 0, right? Then you can conclude that the summation of a sub n is divergent. So this is just from the statement of the divergence test. And we just learned that if limit of a sub n equal to 0 when n go to infinity, so the divergence test is inconclusive. Well, it means you cannot conclude anything from the divergence test. So it means the series could be convergent or divergent. So the common mistake that students always make is when you get limit of a sub n equal to 0, you always conclude that the series is convergent, which is wrong. So when limit of a sub n equal to 0, it is possible that the series is divergent, and one of the example is the harmonic series. Well, this is supposed to be the easiest example when limit of a sub n equal to 0 and the series is divergent. So the harmonic series is of the form summation of 1 over n. Well, if you expand it, it's just 1 plus 1/2 plus 1/3 and so on. So it is clear that limit of 1 over n equal to 0. So it has property that limit of a sub n equal to 0. But when you look at the convergent or divergent property, you're gonna see that the harmonic series is divergent. So let's move down to the proof here. So the theorem says that the harmonic series summation 1 over n diverge even though the terms of the series approach 0. So the proof is here. So you can see that, well, if we assume that the harmonic series converge to a real number L, then we have L equal to 1 plus 1/2 plus 1/3 plus 1/4 and so on. So the next line, I am going to start doing an inequality. So what I did here is just I replace 1/3 by 1/4, and then I replace 1/5 by 1/6, I replace 1/7 by 1/8, I replace 19 by 110. So you can see that this line, the line that I just say, this is inequality star. This is true because you can see that 1/3 is always bigger than a quarter, 1/5 is always bigger than 1/6, and so on. So this inequality star is 2. And then after that, you can see that your L is bigger than 1 plus 1/2 plus 1/2 plus 1/3 plus a quarter plus 1/5, and so on. So after you simplify everything, you're gonna have L is bigger than 1/2 plus L, which is impossible. So it means the harmonic series cannot be convergent, so it must be divergent. Before we start doing some example, let's talk about property of convergent series. So we have 3 properties here. Property number 1. So if you start from a convergent series and you have a constant C attached with it, so keep in mind that you can pull out constant C from the summation, and then the series converge to the value C times A. Property number 2. Well, if you have a convergent series AN that converge to A, and convergent series Bn, summation of Bn, that converge to B, then if you add them up or subtract them, so it is still convergent, and its limit is going to be A plus or minus B. The last thing, so well, when you look at the convergent series, it doesn't matter where you start. You can start from n equal to 1, n equal to m, or n equal to anything. So the answer about convergence and divergence will be the same, because you just switch the point that you start. Well, the behavior on the tail are still the same. So you will get the same property of convergence or divergence. Alright, so now let's do example 13. So example 13, let's determine whether the following series converge or diverge and evaluate if possible. Alright, let's do it. So we're gonna start by looking at this thing. So we can split it into 2 pieces. So this is summation of e to the negative n when n equal to 1 to infinity, plus summation of 1 over n equal to 1 to infinity. So clearly you can see that this is harmonic series, right? This is just 1 over n. So this is divergent. So what is summation of e to the negative n? So if you simplify a little bit, so this thing is equal to just summation of 1 over e to the n, right? N start from 1 to infinity. So this is geometric series that R, or common ratio, is 1 over e, which is less than 1. So that means this series is convergent. So when you have a convergent series, add them up together with the divergent series. So the answer gonna be divergent. So summation of e to the negative n plus 1 over n start from 1 to infinity, this is divergent. So if you add convergent and convergent together, so you get convergent. If you add convergent and divergent, it's gonna be divergent. Alright, so let's move to part B. So we have the series like that. So for sure we need to simplify first. So I'm going to simplify this thing. So I have summation n from 1 to infinity of, so let's pull out number 2. So I have 2 times 2 to the n over 4 to the n, right? And then plus 3 times 3 to the n over 4 to the n. All right. And then after that, I have summation n from 1 to infinity. So I have 2 times 1 half to the n. And then plus 3 times 3 over 4 to the n. All right. Then after that, I have summation n from 1 to infinity of, let's say now I have 2 times 1 half to the n plus summation. So I just split two terms. So 3 times 3 over 4 to the n. You can see that both of them, they are geometric series, right? So this thing is geometric series. Well, the first term a is equal to 2 times 1 half to the 1, which is 1. And then our r is 1 half. And then this is geometric series as well. And then you have a equal to 3 times 3 over 4. And that is 9 over 4. And then my r is going to be 3 over 4. So both series are convergent because our r here is 1 half and 3 over 4. So both of them are less than 1. So, well, both series are convergent. And then now we can compute the limit by just using the formula a over 1 minus r. So the first term converges to 1 over 1 minus 1 half, right? Because this is 1 here, this is a, and then r is 1 half, which is here. And then another term is now I have 9 over 4 over 1 minus 3 over 4, right? Because this is a over 1 minus r geometric series. And once you simplify this thing, so you get to plus 9, which is 11. So I will leave you as an exercise to simplify this thing. So at the end, we know that the series converges to a real number 11. Now let's move to one of the hardest topic in this chapter, which is the integral test. So the integral test is hard to use, I should say. So it is not easy to use because you have to integrate a function as well. So that means you have to come back and use your integration technique sometimes. But it is good to know because some series cannot be determine the convergent pattern by using just the simple geometric series or divergent test. So you have to go by the integral test. So let's look at the idea behind the integral test first. So the idea behind the integral test is that if you focus on just a2 plus a3 plus ... This is a summation from n equal to 2 to infinity. So this is going to be just the box here that I highlight in green. This thing is always less than the area under the curve here, right? The area under the curve here is known as an integral of fx dx from 1 to infinity, right? This is from 1 to infinity. So the area under the curve is known as the integral from 1 to infinity of fx dx. And that thing, it must be bigger than summation of a sub n. N start from 2 to infinity. You can see from the picture here. And then on the other hand, if I just look at the sum start from a1, that will be the stack that I highlight in yellow here. This time, your summation is going to be bigger than the integral from 1 to infinity of fx dx. So from this picture, you can conclude this inequality, right? And then you can see that if the integral converge, then it's gonna force that the series n start from 2 to infinity converge as well, because if this is convergent, right, it's gonna force that this thing is convergent too. On the other hand, if this thing is divergent, it's gonna force that this thing must be divergent too. Well, you will learn this concept more when we hit the comparison test. And the final statement of the integral test is, well, if you want to check the convergence of the series, you can just compute the integral from 1 to infinity first, and the convergent pattern of the series gonna be the same with the convergent pattern of the integral. Well, this is the idea behind the integral test. If you feel like you got lost, that is fine. Just learn how to use it first, so the proof you can catch up later if you have time. Alright, let's look at the statement of the integral test and do some examples. So this is the statement of the integral test. Before you use the integral test, you have to make sure that your function is continuous, positive, and decreasing. Well, you need 3 conditions: continuous, positive, and decreasing. So once you know that your function is continuous, positive, and decreasing, then the integral from 1 to infinity of fx dx and the series an, they will have the same convergence or divergent pattern. So it means they either both converge or both diverge here, as I state here, that I highlight in yellow. Alright, let's do example 14. Alright, I have summation of n over n squared plus 1. So take a deep breath, because this example is long, and you will see that the integral test, it is not easy to use, but it is good to know. So for here, I can say that this is my an, right? So my a sub n is going to be n over n squared plus 1. Alright, so we can say that the function associated with this series is fx equal to x over x squared plus 1. So the first step before you use the integral test, you have to set up your function first, and the function that you set up here, it's going to be the same function as you solve in the problem, right? So you solve n over n squared plus 1, so I'm gonna just copy the function and change it to from n to x. Alright, next we are going to check 3 conditions of the integral test, which is continuous, positive, and decreasing. So first, let's see, f is continuous and positive on the interval 1 to infinity for sure. So this is clear that f is continuous and positive, because f is just a rational function, x over x squared plus 1, so it is continuous always on the interval 1 to infinity, right? And always positive, because you focus on the positive interval. So once you replace x into the function f, so you always get positive number. Now to verify decreasing, so how do you know that the function f is decreasing, so you have to differentiate one time and make sure that this thing is less than 0, right, from count 1. So we're gonna differentiate one time. We differentiate this thing, so we're gonna use the quotient rule. So differentiate x over x squared plus 1. So we have x squared plus 1 times 1 minus x times 2x over x squared plus 1 square. So I use low d high minus high d low over low square, right? And then after that I simplify this thing, so I have on the denominator I have x squared plus 1 square. On the top I have 1 minus x squared. So you can simplify it at home. And then after that, well, to conclude that this is decreasing, so I have to make sure this thing is less than 0 or not. So you can see that on the denominator this thing is always positive, right? On the top this is always less than 0 because, well, you focus now on the interval that x is bigger than 1, right? This is what you focus on now. So x is bigger than 1, so 1 minus x squared is always less than 0. So now you're done with checking assumption. So the function is decreasing since f prime x less than 0 when x is bigger than 1. Well, let's conclude that the function is decreasing. Alright, decreasing. So all conditions for the integral test are satisfied. Alright, now let's integrate this thing. So we're gonna integrate x over x squared plus 1 dx from 1 to infinity, and whatever the answer we have, we can conclude that the series is gonna behave the same way as the integral. So here we're gonna just use the improper integral, so it's gonna be limit of integral of 1 to b and take b to infinity. So x over x squared plus 1 dx. This is from calculus 1, improper integral. And then after that, you can just do limit for when b go to infinity of, well, let's integrate this thing first. So x over x squared plus 1. So you can switch dx to dx squared plus 1 and you get 2x here. Well, just use a substitution. And then after that you cancel 1x. Well, keep in mind that the limit of integration is x equal to b and x equal to 1. Alright, next you have limit b go to infinity. So when you integrate 1 over x squared plus 1 dx squared plus 1, so you get logarithm, right, of x squared plus 1. And now you have to replace x equal to b minus x equal to 1. Alright, so you have limit b go to infinity of, well, I forgot number 2, so the number 2 here gonna just move out, so you have 1/2 in the front too. Alright, you compute this thing, so you get logarithm of b squared plus 1 minus log 2. Alright, and once you compute limit here, so when b go to infinity, so log infinity is infinity, so for sure this limit is plus infinity. So the integral diverge. So the integral diverge. Well, this implies that the series summation of k over k squared plus 1 n from not k, n over n squared plus 1 when n from 1 to infinity is also divergent from the integral test. Well, you can see that the integral test, this is tough to use, but if you want to use it, you have to define your function f, check that the function is continuous and positive and decreasing, and then after that you integrate, and the result that you get from the integration is going to be the result that you use for the series as well. Alright, let's do one more example. Part B. So let's suppose that I want to use the integral test for summation of 1 over n squared plus 4 when n start from 0 to infinity. So again, we need to set up the function. So I'm going to set up my function fx to be 1 over x squared plus 4. So you have to set your function that is similar to, well, the series that is given in the question. Then we can see that f is continuous, right? And positive on the interval 0 to infinity for sure, right? Because on the interval 0 to infinity, because you start from 0 here, from 0 to infinity, well, f is continuous and always positive. So now to check that f is decreasing, what would you do? So it is clear, right? Because, well, when x is getting bigger, x squared plus 4 is getting bigger, and 1 over x squared plus 4 is getting smaller. So that means function f is decreasing. Alright, I'm gonna note it here. So it is clear that f is decreasing on 0 to infinity, because as x go to infinity, the denominator of f is growing big, right? So that means f is decreasing. Alright, now we're gonna do the integration. So let's integrate 1 over x squared plus 4 dx from 0 to infinity. And then this result gonna be the one that we use to conclude the pattern of the series as well. So this is improper integral, so I'm gonna do limit when b go to infinity, integral from 0 to b, right? 1 over x squared plus 4 dx. This is the technique from Cal 1. And then after that you have limit b go to infinity, 0 to b. Now we have 1 over x squared plus 2 squared dx. And then if you remember, when we have 1 over x squared plus a squared, so this thing gonna integrate to arctan. So I have limit b go to infinity, so integrate this thing, I have 1/2 arctan x over 2. So this is the integral of well, this is 1 over x squared plus a squared. This is the antiderivative of arctan, right? Well, just from calculus 1. And then this thing is 1/2 times arctan x over 2. And then you need to replace x equal to b and x equal to 0 at the end. So you have limit b go to infinity, and then you have 1/2 arctan b over 2, right? And then minus 1/2 arctan 0. Well, arctan 0 is always 0, so this thing go to 0. And then arctan b over 2 when b go to infinity. So the graph of arctan is like this. Alright, this is the graph of arctan. So when x go to infinity, so arctan x go to pi over 2. So this means this term goes to pi over 2, right, as b go to infinity. So this thing go to pi over 2, and then you multiply 1/2. So this thing go to pi over 4, which is convergent, right? Because it is less than infinity, so this is convergent. So to conclude this thing, so we're gonna say that since integral of 1 over x squared plus 4 dx start from 0 to infinity converge by the integral test, the series 1 over n squared plus 4 n start from 1 to infinity is also convergent as well. And that is how we do the integral test. To wrap up this section, we're gonna talk about the p-series. So the p-series is super easy to use, and we obtain this thing from the integral test. So let's look at the statement of the p-series. So the p-series is of the form 1 over n to the p. So if you see the form like this, for sure you can conclude the convergent and divergent pattern by just using this theorem. So for the p-series 1 summation 1 over n to the p, it is convergent if p is bigger than 1, and it is divergent if p is less than or equal to 1. So when you do the problems, you just need to simplify until you hit the form 1 over n to the p, and then after that you can conclude it by using the p-series. So we will do this example quick. So let's do example 15 together. So use the p-series test. So number one, I have this series. So this is summation of 1 over n cubed, n from 1 to infinity. And here we go. You can see that here p equal to 3, right? Because this is p-series with n equal to 3. So which is greater than 1? Well, it means the series is convergent. That's it. That's it. Easy like that for this topic. And then for part B, now you have summation of let's say you have 1 over n raised to the 3 over 4, right? Because that thing is the fourth root of n cubed, so it is n raised to the 3 over 4. So that means here you have p equal to 3 over 4, which is less than 1. So it means the series is divergent. Right, easy like that. All right, the last one, let's look at summation of 1 over n minus 1 square n equal to 4 to infinity. So it is not clear at first what is this series. So we're gonna expand it first. So if you expand it, so let's see what it is. So the first term is going to be 1 over what? So replace n equal to 4. So the first term is going to be 1 over 3 square. The second term replace n equal to 5, so you get 1 over 4 square. And the next term is 1 over 5 square, right? And so on. So actually this is what? So you can just add 1 over 1 square, 1 over 2 square, right? 1 over 3 square, 1 over 4 square, and so on. You can add the first two terms in and then subtract the first two terms. Does it make sense? So I just add this two term in. So I have to subtract this two term out as well. So the equality still holds. And then you can see that the first term here that I just use the big parenthesis here. This is going to be summation of 1 over k square. Oh, sorry, 1 over, let's use n. 1 over n square, n equal to 1 to infinity. Right? And then minus some constant. Well, this is just constant. Right? This is just a constant. Well, I will use another color so to give you the idea. So this is just some constant, right? And this is just the series. This is the series. All right. Well, you can see that this thing is P series, right? With P equal to 2. So this is convergent. So when you have a convergent series and then you subtract just some constant or some number, so well, it does imply that the main series is still convergent. So to conclude this thing, so we're gonna say that summation n start from 4 to infinity 1 over n minus 1 square is convergent, right? Because, well, the P series is convergent and then you subtract constant, it is still convergent. All right, and that is the end of this section. So I would say this section is tough because, well, the integral test is hard to use. Well, but don't worry about integral test much, because if I ask you to do on the exam, I will state clearly that use integral test. All right, we're gonna stop it here and see you on the next video, section 1.5. Bye.